Good day, Mom. Our topic is all about elliptic geometry. So first, what is elliptic geometry? So elliptic geometry is one of the three classical non-Euclidean geometry along with hyperbolic geometry. So elliptic geometry is one of the examples of non-Euclidean geometry together with hyperbolic geometry and spherical geometry. And elliptic geometry studies the geometry of elliptic objects. So as you can see on the left side, there is a figure. And that figure is an example of elliptic objects. That is an elliptic object. This geometry that has no parallel lines because all lines eventually intersects. So we cannot see a straight lines that are parallel because in elliptic geometry we can only see a curved lines that always intersects and they are not parallels. Then triangles in elliptic geometry has angles that sum to more than 180 degrees. In elliptic geometry, the triangle must sum to more than 180 degrees. So the measure of the triangle must be more than 180 degrees. Elliptic geometry is a non-Euclidean geometry that studies the geometry of spherical surface like Earth. Like what I'd say, elliptic object is somewhat like an Earth shapes. It is also known as Riemannian geometry, named after the German mathematician Bernhard Riemann. Elliptic geometry versus Euclidean geometry. Elliptic geometry studies the geometry of curved objects like spheres, while Euclidean geometry studies the geometry of flat, non-curved objects. A postulate in geometry is a statement that is assumed to be true without any requirements of proof. When looking at a flat object, like a piece of paper, in Euclidean geometry, it is possible to draw parallel lines on it. So, in a piece of paper, we can draw two straight lines that are parallel. Parallel lines are straight lines that are always the same distance from each other. In Euclidean geometry, there is a parallel postulate that is used when working with parallel lines. So, the figure given, that is an example of Euclidean geometry because we can see there is two straight lines that are parallel. So, if you try to do this in a curved objects, it is impossible to draw straight lines because in a curved objects we can only draw curved lines, right? Curved lines that are not parallels. So that curved object is an example of elliptic geometry. Euclidean geometry is a geometry of flat surface. Any geometry that violates the parallel principle is known as non-Euclidean geometry. There is a few different types of non-Euclidean geometry and one of it is our topic, which is the elliptic geometry. Next is elliptic geometry is a non-Euclidean geometry in which a given line A and a point A outside A passing through A, as all lines in elliptic geometry intersect. The next topic is the postulate of elliptic geometry.
Elliptic geometry postulates. The following are postulates in elliptic geometry. There are no straight lines. There are no parallel lines in elliptic geometry. The sum of the interior angles of triangle is greater than 180 degrees. Postulate number 1. There are no straight lines. Therefore, the line drawn on curved surface like a sphere are always curved. So, in this illustration, line A and line B is a curved line. Postulate number 2. There are no parallel lines in elliptic geometry. There are no parallel lines in elliptic geometry because any two lines will always intersect at the same point. An example of this postulate is the longitude of the Earth. So, this illustration is an example of the postulate number 2. P and Q will intersect at the same point of O. Postulate number 3. The sum of the interior angle of a triangle is greater than 180 degrees. So, prove angle A plus angle B plus angle Y is greater than 180 degrees. So, in this illustration, show that if angle A is 50, angle B is 60, and angle Y is 90. So, if the sum of these three angles is combined, is equals to 200 degrees. So, it conclude that 200 is greater than 180 degrees.
Hello everyone, my name is Sarah Mirafuentes, and today I'll discuss to you guys the 4 important topics in elliptic geometry, which is called axioms. My part will focus on the 4 theorems that shape our understanding of elliptic geometry. So, there are some theorems in elliptic geometry. The theorem 1 is the segment joining the midpoints of the base and the summit is perpendicular to both. So, I have here an illustration. This one. This illustration proves that theorem 1 exists. So, the segment joining the midpoint of the base, our segment here is C and D. And our midpoint here is M. And our base is here. And so these are the segment joining the midpoint of the base. And it says that in theorem 1, the summit is perpendicular to both. What is the summit, by the way? The summit is the vertices opposite equal sides. The summit here is the C and the D. Okay, so the perpendicular in this illustration is line CT is perpendicular to line MM. Understand? Again, in theorem 1, the segment joining the midpoint of the base and the summit is perpendicular to both. So here is here. Now this is perpendicular to this, and this is perpendicular to this. Theorem 2. This is my illustration here. So the summit angles of a Sagittarian quadrilateral are congruent and obtuse. Again, in theorem 2, the summit angles of a Sagittarian quadrilateral are congruent. Here, we obviously see the congruent sign. And obtuse. Here, this, and this. In our theorem 3, I have here an illustration. The theorem 3 states that the sum of the measures of the angle of any triangle is greater than pi. Our theorem is debatable, and we can think that in this illustration, the sum of the measure of the angle of any triangle here is greater than 280 degrees. This is what we call the theorem 3. In our theorem 4, the sum of the measures of the angle of any quadrilateral is greater than 2 pi. Okay? In our illustration here, we have 4 sides. So this one, 1, 2, 3, and 4. illustration that is greater than 2 pi or greater than 360 degree is what we call this theorem 4. To explain further my part, I have here an example of each theorem. So first, let's discuss about the theorem 1. So in this illustration, let E and F be the midpoint of AB and CD respectively. Construct EF. Note EF perpendicular to AB and EF perpendicular to CD. Construct EF and BF. So, in this illustration, by using the SAS congruency or the side angle side congruent, we have triangle ADF is congruent to triangle BCF, and our line here is AF congruent to BF. Another is by using the SSS congruency or the side congruency, we have triangle AEF is congruent to triangle BEF. Angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4, and angle 5 is congruent to angle 6, and the angle 1 plus angle 6 is equals to angle 4 plus angle 6. And lastly, the angle DEF is congruent to angle CFE. Yan, the theorem 1 exists, right? So our midpoint, our segment here is DC, and joining the midpoint of F, and our base here is in the lower part, and the summit here that is perpendicular to both is DF. The line DC is congruent to, line DC is perpendicular to line FE, right? So here, in example, the theorem 1 exists. In our theorem 2 example, here, angle ADC is congruent to angle BCD, while the angle BDC is congruent to angle ACD. Construct line AC and BD. So, by using the SAS congruency or side angle side, we have triangle ABC is congruent to triangle BAD. So, we know that in this theorem, the summit angles are congruent. So, as we can see in the illustration, we have here an congruence. So, the Sachar quadrilateral is ABCD, right? So, this is quadrilateral since it has 4 sides. So, our quadrilateral here is ABCD. So, before we proceed into the theorem 3 example, we have here a lone. A lone is the part of the surface of the sphere bounded by the arcs of 2 great circles. So we have here the formula. L times theta is equals to 2 theta r square. So 4 pi r square plus 4a is equals to 2l times a plus 2l times b plus 2l times y if triangle ABY A is equals to 2 pi r square plus 2a is equals to L times a plus L times b plus L times y. So 2 pi r square plus 2a equals 2ar square plus 2br square plus 2yr square. So 2 pi r square plus 2a is equals to 2r square times a plus b plus y. So since they have the same in the equation, so our 2r square is in outside and we parenthesis the a plus b plus y. So n plus a over r square is equals to a plus b plus y. So a plus b plus y greater than pi is our answer. So, what's the connection of this example in our theorem 3? So, in our illustration here, the sum of the measures of the angle of any triangle is greater than pi. So, our theorem is sabotable because any triangle here that we see in this illustration that greater than pi, or what we call greater than 180 degree, is theorem 3. In our theorem 4 example, construct AC, triangle ABC and triangle ACD are elliptic triangles. The sum of angles of triangle ABC is greater than pi. Similarly, the sum of angles of triangle ADC is greater than pi. It follows that the sum of angles of ABCD is greater than 2 pi. So, in our illustration here, so this is what we call quadrilateral. So, quadrilateral means quadrilateral means have 4 sides. So here, line AD, line AB, line BC, and line CD. So in our theorem 4, it's similarly in theorem 3, but the difference between them is the theorem 3 is any triangle that greater than pi or 180 degree is what we call the theorem 3. While in the theorem 4, the sum of the measures of the angle that any quadrilateral, since in theorem 3 is any triangle, here is any quadrilateral that greater than 2 pi, or what we call the 360 degree, is of this theorem 4.
Elliptic geometry is a non-Euclidean geometry with positive curvature, which replaces the parallel postulate with a statement: from any point in the plane, there exist no lines parallel to a given line. In order to achieve a consistent system, however, the basic axioms of neutral geometry must be partially modified. Most notably, the axioms of betweenness are no longer sufficient, essentially because betweenness on a great circle makes no sense. Namely, if A and B are given in a circle, and C is between them, then the relative position of C is not uniquely specified, and so must be replaced with the axioms of subsets. What is the use of elliptic geometry? Elliptic geometry can be used to calculate the shortest distance between places that are far away from each other. Examples: airlines and pilots can use it to calculate the best route between two cities, and ship captains can use it to calculate the best route between two harbors. Elliptic geometry is also used in space exploration and cosmology.